All right. Well, I will begin with a word of prayer. I will soon begin with a word of prayer. There you go. Dearly Father, we thank you for this day. Thank you for being inside at the moment. Help us to learn more about your creation together, Lord. In your name I pray. Amen. All right, so I have a few examples, which I have already put on the board. And so I think the thing that unites these examples is, of course, that they have some kind of radical that we'd like to get rid of. So let's just begin. So this one here, I look at this and I go, well, I think if I make an x equals to 3 sine theta substitution, that'll be smart here. You're like, well, why would you do that? Because if I do set x equals to 3 sine theta, what does the thing inside the radical become? What's 9 minus x squared be with this substitution? Right, so we can factor the 9 out. What's 1 minus sine squared theta? Cosine squared, yeah. So we've got 9 cosine squared theta, right? So, therefore, square root of 9 minus x squared is equal to square root of 9 cosine squared theta, which is equal to 3 cosine theta. So that is a nice simplification. And then how about dx? Looks like 3 cosine theta d theta, yeah? Now, one thing that you might worry about that we haven't worried about is when I take the square root of 9 cosine squared theta, it should be what? It should be positive, right? I mean, or non-negative, right? Square root of a quantity should be non-negative. But cosine of theta could be negative if you put the wrong theta in, right? So why would you expect that 3 cosine theta is a positive quantity here? How was theta defined? I mean, essentially this triangle tells you everything. This is theta. Sine theta is what? X over 3. So the opposite side is x. The hypotenuse is 3. And here you've got square root of 9 minus x squared, right? So if you look at that triangle, it seems pretty reasonable to suppose that cosine of theta is going to be non-negative, right? So I haven't belabored this point last class because pretty much I don't really know of an example where that square root has to be treated with more nuance. Just always put what you think, kind of expect, yep.
How did you figure out why set x equals 3 sine theta?
Indeed. All right, so let's see here. So last time I made everything work out to 1, right? So let me write down a series of identities here that'll kind of explain it to you. So, of course, we have cosine squared theta plus sine squared theta equals to 1. We also know that cos squared theta minus sinh squared theta is 1. And then we have the close cousin identities. You got your tangent squared theta plus 1 equals to secant squared theta. And I think that ought to do it for us, right? I mean, there's also a hyperbolic one. Fine. Tangent squared theta minus 1 equals the hyperbolic secant squared theta. So I can take any of these, right? I can take any of these and multiply by a squared. And what's that give me? It gives me things like, a sine theta squared equals to a squared minus a squared cosine theta. Rather a squared. I also get that a squared cos squared theta is equal to a squared plus a squared sinh squared theta. I can also derive that a squared tangent squared theta is equal to a squared secant squared theta minus a squared. Are there any other little identities we could derive relating a square to a sum or a difference of squares that might be convenient for us? I guess I've solved for sine squared, I've solved for cos squared, I've solved for tangent squared. I guess I could solve for secant squared, right? A squared secant squared theta, what would that be equal to? Oh, just a squared tangent squared theta plus a squared. So make a little box here. So she's asking how I knew to put x equal to 3 sine theta, right? So what I'm right now doing is listing all your flavor options, right? Or the 4 dominant flavor options. There are 4 choices of x, yeah.
Is there something called squared with the cosine in that first?
Oh, yes. Thank you. No. Yeah. So the first row corresponds to the choice of x equals to what? Here I have x equal to, I would be putting x equals to a cosine theta. And then this pattern would actually tell me what? A squared minus x squared equals to? A squared sine squared theta, right? If I put x equals to a sinh theta, that gives me the following pretty nice identity, which is that a squared plus x squared equals to a squared cos squared theta. The difference between what I'm doing right now and what I did last time is last time I always forced myself to have like 1 plus cosine or 1 minus sine squared or 1 plus cos squared, right? But you don't have to do that. You can make a substitution which just multiplies the cos, the sinh, the sine, the tangent, whatever, by a number, right? So this is another level of the thinking. So here I would put x equals to, what we got, a secant theta. That earns me the following substitution. That earns me that x squared minus a squared is equal to a squared tangent squared theta. And finally, the last one would correspond to a choice of x equals to a tangent theta. And that earns me the following substitution, that x squared plus a squared is equal to a squared secant squared theta. So this is how I know to make x equal to 3 sine theta. I know that making that substitution will make the thing under the radical become a square. The 3 has to go next to the sine to match the 9 that's already there. Yeah? Now, these are not overlapping, right? I mean, excuse me, they're not mutually exclusive. You notice that the x equals sinh and the x equals a tangent theta, these are in competition for a certain class of problems, right? Like the second and the fourth one here, they could attack the same set of problems. Which one's better? Well, that kind of depends on the details, right? They would leave you with different integrals to deal with, either one in hyperbolic terms, one in trigonometric terms. But again, it always goes back to manipulating these basic identities to reduce the thing under the radical to be a square, same as yesterday. To complete my table, you might also put down what's dx in each of these cases, right? All right. So, what do we got? Does that answer your question? Okay. So 3 cosine theta. But, I mean, that question you asked, that is the main thing that you're going to get stuck on with trig substitution, right? Not knowing where to start. There is no, I mean, that box I just wrote over there is sort of the analog of Liate here. It's a little bit more nuanced than integration by parts, isn't it? I don't know. I personally enjoy this more, but okay, so dx is 3 cosine theta d theta. X squared was what? 9, yeah, 9 sine squared theta, right? What's the square root of 9? That's the, oh, check that out. See that? So the 3 cosine theta d theta, let me see the 3 cosine theta from the dx and the 3 cosine theta from the root, they both cancel. And what does it leave us with? Looks like 1/9. What's 1 over sine squared? It's not secant, but you might have said cosecant. I can't hear. Cosecant squared theta d theta. What's the integral of cosecant squared? I heard a minus cotangent. If you're uncertain about that, what should you do? And this should take every student here all of about a half a minute to check, right? What do? You're like, I Google it. Well, not allowed on the test. This is not the online version, right? Let's see here, cotangent. Oh, I'm sorry, did I say that? Let's see here, d d theta. What's cotangent? Yeah, cosine over sine. And so then what do? Quotient rule, right? So derivative of the top, which is minus sine theta, times the bottom, which gives me sine squared, and then I get minus cosine squared theta, because the derivative of the bottom is cosine minus the top, right? F prime g minus f g prime, which gives us sine squared plus cosine squared with a minus out front. And then downstairs, sine squared theta. Of course, that is minus 1 over sine squared theta, aka minus cosecant squared theta. So, indeed, the antiderivative of cosecant squared is minus cotangent. And then what? All right, great. And then we should use the triangle, right? We'd like to write our answer as a what? As an algebraic function. So what would that be here? What's cotangent theta? It should be the hypotenuse. No, wait a minute. Tangent's what? Opposite over adjacent, right? So the cotangent is adjacent over opposite, which in this case is square root of 9 minus x squared over x. And so here you go. Minus the square root of 9 minus x squared, all divided by x, plus a constant. There you go. That is the answer, is a algebraic function. Now, suppose for some reason you forget the triangle of the substitution, right? What's an alternative answer that would give you partial credit? Yeah. Yeah, go ahead. Oh, still the marker. I mean, the minus is there, but the 9 is hard to find. Yeah. Thank you. Yeah. Theta is what? So, yeah, you guys are telling me inverse sine of x over 3? Right. So a much uglier form of the answer would be minus 1/9 cotangent of inverse sine of x over 3. Right? Ugly. Hideous. Don't look at it. No. You know, if this happened to be the answer to a model that you're designing and you're coding something for, which do you want to use? I think that the formula above would probably make a better template for setting up some computer code, right? Like if you got to calculate this, you have to reference 2 rather complicated functions that are in like the function library of whatever you're coding in. And this is just a finite sequence of elementary operations. You should make that go faster. It's a better formula. Anyway, we'll come back to this one. Example 2. All right. So what does this remind us of? To me, this reminds me of tangent squared theta plus 1 equals secant squared theta, right? So if I think about 4x squared plus 1 being equal to this, that suggests that I should make 4x squared equal to tangent squared theta, right? I'm not deriving this. This is educated guessing, yeah? So what should x equals to what here, for example 2? I heard x equals to what? Tangent over 2, yeah, tangent theta over 2. Or, if you'll allow me to erase my thought bubble. Poor planning on my part. All right, let me just, curses. Oh, man, I have worked myself into a corner, literally. Let's see here. So, have we all seen this? So I'd actually prefer to write the substitution like this, 2x equals to tangent theta. And I know that's the same as what you guys just told me, but it has certain advantages to think this way, because then tangent squared theta plus 1 equal to secant squared theta reveals that 4x squared plus 1 is equal to secant squared theta, right? And that's what we're facing, 4x squared plus 1, right? So this says, among other things, that the square root of 4x squared plus 1 is equal to secant theta. This is very nice. And how about dx? Well, fine. Now, I'll divide by 2. X is 1/2 tangent theta, so dx is what? 1/2 secant squared theta d theta. Like, I don't like the way you do details. I do details different. Great. Think for yourself. This is wonderful. You do not have to do the details exactly the way I do. But what you do have to do is show me details. Okay, so here we go. What's dx? 1/2 secant squared theta d theta. And we're dividing by, apparently, secant theta. Oh. It looks like a prophecy has become true. What has happened? What did I tell you? What happened? This is number 1. This is our first encounter with secant theta after the introduction of secant theta. I predicted there would be at least 6. There's one down. All right. If I don't get to 6, I guess that makes me a liar. You don't care? Yes?
How do you get secant theta on the denominator?
The square root of 4x squared plus 1 is the square root of secant squared theta, which is secant theta. Yeah. So by design of the substitution, short answer. What's the integral of secant theta? Well, we worked this out the other day. It is the natural log of the opposite value of secant theta plus tangent theta plus a constant, right? I'm going to have to, there we go. So moving along here, what is secant theta and what is tangent theta in terms of x? What's the triangle of this substitution? Tangent theta is 2x, right? So if tangent theta is 2x, that means that we could, you got various options, right? But one thing you could do, you could put 2x here. You could put 1 here, since tangent theta is 2x over 1, right? If you use your imagination, you can see that, right? So we got the opposite side is 2x, the adjacent side is 1. What's that make the hypotenuse by the Pythagorean? Hey, what do you know? That's the thing we were trying to get rid of to start with. So that happened again. That often happens. We've only seen one example where that didn't happen so far. And then what? Oh, so there's tangent. Tangent theta is 2x already, right? I should just write that. We already know tangent theta is 2x. That was, that's not up for grabs. So I don't know what secant theta is yet, but tangent theta is definitely 2x. And what did you say secant theta is? It should be hypotenuse divided by adjacent, right? What's that? Oh, did I already derive it? Oh, it's already here. Yeah, sorry. This doesn't always happen, so I usually write the triangle just to make sure I've got everything I could possibly need, right? I could skip writing the triangle here fine, and you'd still be, like you pointed out, it's already in my thought bubble, what I need, right? But the reason I'm drawing the triangle is there's a whole other set of problems where the triangle is needed because you haven't already found the algebraic expression for the trig function that comes up in the answer. So it might seem like I'm trying to make the problem more complicated than it is, but actually I'm just trying to help you. All right, so square root of 4x squared plus 1, and then tangent theta we said was plus 2x plus a constant. There you go. That's the answer as much as we can in terms of algebraic functions. How can we make these problems more complicated? You don't think I can? Well, that sounds like a challenge. This problem could come to you looking like e to the x dx over, I don't know, e to the 2x square root of 9 minus e to the 2x. It could look like that to start with. That's this problem again. Or you could face something like the integral of dx over x minus 3 squared, square root of 9 minus x minus 3 squared. You could have something like that happen to you, right? If you multiply this out, what would that be? Really? Cool. So I can replace that with 6x minus x squared. I mean, what I'm trying to say is you could face these patterns, but first you have to complete the square before you can unravel them. I did some of those last class, right? So the ones I'm looking at this class are a little bit simpler in the sense that there's not the completing the square aspect to the simplification at the start, right? But that could happen. How about this one? This one's the same as example 1. You just have to make a what substitution? Yeah, make a u substitution. If you make a u equals e to the x substitution, then this becomes the integral of du over u squared times the square root of 9 minus u squared, which is the problem we solved. Right? There's some problems like this in your homework. Don't be bullied by them. They're not that bad. You just have to make a substitution at the start to convert it to plain Jane trig substitution problem. And similar comments apply over here, right? I mean, it could be that you have to complete the square before you get to something like this, right? I mean, there's a family of problems like this, or it could be, let me stop. This is not a happy place for you guys. Let me go away from it. Probably the conversation, how can I make this problem harder? Well, I mean, it's a conversation you'd actually like for me to have with you because that might be helpful to you. But it's uncomfortable, so we'll go on. All right, so this one here is an important example because up to now, oh, you'd think I'd learn by now not to talk where you've just sprayed the stuff. Because talking involves breathing. And breathing board cleaner is always a losing proposition. There's no kind of high or anything like that. I have been meaning to start vaping, you know. It seems really cool, doesn't it? I mean, am I wrong? No? So I tell you, I may have told you guys this before, but the first place I ever saw it was at Medieval Times. We went on a trip to Disney World a few years ago, and maybe like 5 years ago, and we were watching the. So Medieval Times, like, if you're good at bar fighting, right? Like, what should you do? Obviously, Medieval Times. That is your calling. It's where you should be working, because there you fight other people, or fake fight other people for a living, pretty much, right? It's pretty. There's not so many jobs where you can do that, right? It's maybe like kind of like rodeo clown is sort of in that family of jobs. These jobs are hard to find, right? But anyway, I was sitting there watching the people fake fighting each other, riding their horses, and so forth and so on, where we were eating our half chicken they gave us or whatever. And then the guy in front of me, all of a sudden, there's this like cloud of wonderfully scented whatever wafting out. And I thought, how's he smoking in here? And I was like, wait a minute, that's not smoking. It's better than smoking. That is so cool. It's like cool. I should be doing that. Then I would be cool. But my wife won't let me start, so what do you know? See, if I was already, I guess I need to start smoking first, so then there'll be a health benefit, right? No? Is that, no? We're also not allowed to vape on campus, right? I think it took us about a year to figure that out, though, right? I mean, oh, okay. I'm sorry. I seem to have erased my my lifeline here. So you guys are gonna have to tell me what should I do. X equal to what? What's that? X equal to? I heard an x equals to secant theta. Square root of 3 secant theta. I like that a lot. If I do that, then what's x squared minus 3? That would be square root of 3 secant theta quantity squared minus 3, which gives me a 3 times secant squared theta minus 1. What is secant squared theta minus 1? I heard a tangent squared. All right. So this is a wonderful suggestion that you guys have made. Because now the difference of terms under the radicals become a single squared thing, which means what? We can get rid of the radical, right? So the square root of x squared minus 3 is root 3 tangent theta. Yay. So this is going to be the integral of, looks like, root 3 tangent theta divided by, what was x? Oh, root 3 secant theta. And how about dx? What's the derivative of secant? It's secant tangent, yeah? So we've got dx is root 3 secant theta tangent theta d theta. All right, well, that's a start now. So the root 3's canceled. Does anything else cancel? Secant thetas cancel. Oh yeah, these cancel. So it looks like we've got root 3 tangent squared theta d theta. Now, there's something I told you before, which is what? We cannot begin by writing a definite integral and then midway be writing indefinite integrals. This is incorrect. In other words, what I have on the board right now is unfinished. When we're doing a substitution, if there are bounds, right, if there are bounds on the integral that we write, we must change the bounds. You have to follow how the bounds change with the substitution. So how does that work here? In other words, if x is equal to 2, then theta equals to what? Right? Let's call that theta 2. Well, let's just say theta equals to what? And vice versa, if x equals to root 3, right, root 3, then theta equals to what? So what are we trying to solve? We are trying to solve 2 equals to root 3 secant theta. And also we're trying to solve root 3 equals to root 3 secant theta for the upper and lower bounds respectively. So what you got here? This gives us that 1 over secant theta, which by the way is cosine theta, is what? Root 3 over 2, right? And on the other hand, this will lead us to the fact that cosine theta is equal to 1, right? Now I converted these to cosine equations because we know how to think about cosine, right? If you've got your handy-dandy scientific calculator, can you find the inverse secant function on there? I mean, it might be in there somewhere, but definitely there's an inverse cosine just sitting there waiting for you to punch, right? So cosine is a better choice. We know how to work with cosine. When is cosine root 3 over 2? Pi over 6, right? So that makes the upper bound become pi over 6. And the lower bound, when is cosine of theta 1? 0, right? So the lower bound becomes 0. Now we're off to the races. What's the integral of tangent squared theta? Well, let's swap that out for a... What was tangent squared in terms of secant squared? What was it? It was secant squared theta minus 1, am I right? Right? Wrong? Yep.
So if you were to like make the substitution, but then reverse
you could erase the bounds from the start of the problem, do the problem as an indefinite integral, find the antiderivative, and then apply the fundamental theorem of calculus part 2 as a final and separate step. Then you wouldn't be wrong. You could find other notation, but the one thing you can't do is change the integral to d theta and still write root 3 and 2 there. That's just wrong. So, I mean, there are other choices, but you have to confront it. This is one of the most common places where calculus students write something they don't mean. Like, you guys will write stuff on the paper. That's not really what you mean, because you never like act on what you write. Usually, every so often, I'll find a student who writes something like an in-between wrong step. I don't know, maybe they walk away from the paper, come back, and then just do what's written, and then it's wrong. You know, so we must change bounds. Okay, there are other, there are various theoretical questions as well which require changing bounds, and if you don't have this in mind, you won't really be able to understand. We'll see this when we study separation of variables in here. There's a place where changing bounds is needed because, like, on the one side you might have the bounds having the meaning of velocity, on the other side you might have the bounds having the meaning of position, and you'd like to change from one to the other in order to, anyway, I'll shut up. We must change bounds. So, and then what? What's the integral of secant squared? Yep. Uh-huh.
How did you get from the 1 over secant equals cos theta equals root 3 over 2 to finding out that the bounds are
Oh, because cosine of theta be root 3 over 2 implies that theta is equal to pi over 6. And if cosine of theta is 1, that says that theta is equal to 0. At least these are choices. I mean, there's infinitely many solutions to those, but those are the ones we want. I suppose for geometric reasons. Just thinking about, we want cosine to stay positive. So if cosine goes from 0 to pi over 6, that's a place where it's positive. That's a good choice of the theta parameter. So the integral of secant squared is tangent. And so we got here is root 3 tangent theta minus theta evaluated from 0 to pi over 6. And so we're looking at root 3 tangent pi over 6 minus pi over 6 minus tangent of 0 plus 0, I guess. Well, find minus 0. Minus a minus 0 there. You happy? Anyway, the lower bound is, nothing to it, right? What's tangent of pi over 6? So we got what? Yeah, sine pi over 6 over cosine pi over 6, which I think you guys told me a second ago here. Sine of pi over 6 is a half. Cosine of pi over 6 is root 3 over 2. So it looks like we get root 3's are canceling on the first term. The halves cancel, so this becomes 1 minus pi root 3 over 6 if I haven't miscalculated. Any questions? Let's look at an applied problem. Well, is it not super applied? This is a problem that you might have faced in Calculus 1. All right. Well, there's a reason that you would not have faced this problem in Calculus 1. All right? I'll let you tell me the reason here in just a second. So let's find the area bounded by 2x squared plus 9y squared equals to 1. So what are we looking at here? If you put this into the usual sort of standard form that I think about anyway, it would look like this. So this is a what? It's an ellipse, right? With what I usually call A equal to 1 over root 3 and B is equal to 1/3 here. Yeah? And so this is just to put it in standard form. That's all. You don't have to do that. I mean, whatever. If you remember, though, the A and the B formulation of the ellipse, maybe it's helpful to you. I don't know. Nevertheless, here's a picture. Let's see here. So x goes like plus or minus 1 over root 2, right? Y goes to like plus or minus 1/3. So roughly speaking, this area we're trying to calculate looks something like this, right? Sort of footballish oval. Seems appropriate. So, okay. So how are we going to find the area? So what I do is I think about chopping it up into little... So this dA will be 2y dx, right? Where y is this. And what is that y equal to? So y squared is 1/9 times 1 minus 2x squared here, right? So we can solve for that y in the upper first quadrant where y is positive. We get 1/3 square root of 1 minus 2x squared, yeah? And so what's the integral we ought to be doing? To find the area. What were the x-intercepts again? This is 1 over root 2, right? And over here was minus 1 over root 2. So we can draw this vertical strip ranging from x equals minus 1 over root 2 to x equals to 1 over root 2. And to add those up, we integrate, right? This hopefully was the first application of integration maybe that people shared with you. I mean, it's the first I would share with students anyway, I think. It's been so long since I taught Calc 1, it's hard to say. Area, so 2y dy, which is in this case 2/3 square root of 1 minus 2x squared dx. Can we clean this up? Is there anything can we make life easier? Yep. There's a 2 in the dA. Because it's, yeah, it's fine. But what else could I do? From 0 to 1, yeah, exactly. That would make life easier. And I'll put a 4/3 out front to be fair to that. And so now I'll ask you the question I asked again at the start of this, which is, a comment I made, which is this wouldn't have been asked you in Calculus 1. Why? At least not to complete the problem. Simple reason. You didn't know how to calculate the antiderivative of that, right? Because it's a trig substitution. So what trig substitution should we do here? I think we want 2x squared to be equal to, sine squared theta, yeah? In other words, let x equal 1 over root 2 sine theta. And if we do that, what's this become? Well, let me write it out. So what's 1 minus 2x squared then is 1 minus sine squared theta, which is cosine squared theta. So this becomes the square root of cosine squared theta. What's my dx? It's cosine theta d theta over root 2. So that's 4/3 integral cosine squared theta. I'll pull the root 2 out front. Cosine squared theta d theta. What about the bounds, though, right? So again, I need to change the bounds. The last two things I wrote are not correct yet. They're a work in progress. I need to put bounds in. What would the bounds be? So x equals to 0 implies theta equals to what? Right? So we have 0 is 1 over root 2 sine theta. So therefore theta, I think 0 will work, right? So actually 0 stays 0. How about the upper bound, though? The upper bound, we have x equal to what? 1 over root 2, which is equal to 1 over root 2 sine theta. So what's that say theta equals to for the upper bound? The neat thing about theta here is it happens to match its geometric meaning in terms of standard angle. Actually, theta equals to 0 corresponds to this. Well, oh, it's not quite that. It's not standard angle. I take it back. Theta equals 0 is like up here. Oh, let me shut up. I don't know what. Forget about that. Look at the formula. So 1 over 2 equal 1 over 2 sine theta. What's sine theta? What's theta equal to there? Yep. Because we doubled it, we changed 2/3 to 4/3. You know, so we're just saying, essentially the formula on the board says that you can quadruple the area of this quarter to get the full thing, which is how some of you might have been taught. Listen, that's pi over 2, right? Pi over 2 gives me the upper bound, so that we change the upper bound to pi over 2. And then you can finish the problem from here, right? Really, this problem would be almost the same if you replace 1 over root 2 and 1 over 3 with just a and b, right? How would you do it if you had a and b there instead of 1 over root 2 and 1/3? What if you just had arbitrary a and b here? How would you do it? Well, you should work on that. That is one of your homework problems. So, anyway, this is nearly your homework problem, but you need to do it for a and b instead. But anyway, I shut up. So, have a good day, guys. Tomorrow, partial fractions.